talking about how we measure energy expenditure. Okay, so here we're going to talk about RQ and RER, and then what we can do with RER. Okay, so RQ and RER are essentially the same thing. So respiratory quotient is just a relationship or a proportion or a fraction, however you want to look at it, of how much oxygen is being consumed and how much CO2 is being produced. Okay, and in order to do this, to get an actual respiratory quotient, you'd have to measure arterial and venous blood gases. Now, this is difficult, but it's not impossible. In our lab here, we do not have the ability to do this, but some exercise science labs do. Like at Oregon, I have the ability to do this if I wanted to, but we never did. We measured blood gases, but never for this reason, because we could just do something else. We could measure RER. And so RER is the ratio of VCO2, or carbon dioxide production, to oxygen uptake. And we measure this at the mouth. Okay, and it's essentially like the VCO2 and VO2, that's what we were calculating on the previous lecture. And so we use this to estimate RQ. Now, the thing to know about RER is it's only useful at steady state conditions and really under submaximal conditions. Okay, and we're going to get into reasons why that's the case, why we can't use it on, or why it's not good if we're not at steady state, and why it's not good if you're at maximal conditions, because this RER number can get a little skewed. And another nice thing about RER is that we can use it to estimate fuel consumption. And what we mean by that is, well, what kinds of fuels or what proportions of fuels are being used? So is it 100% fat, 100% carbs? Is it more fat, more carbs, something like that? Okay, so using chemistry, and we're not going to really dive into that, RER, if we're just using fats, okay, for energy, our RER will be 0.7. If we're just using carbs, it will be 1.0. One thing that's important to understand about RER is that we just ignore protein oxidation. And remember, we don't use a lot of protein for fuel, but we do use some. RER just completely discounts that. Now, it's also possible that RER can drop below 0.7, and this happens if gluconeogenesis is occurring, and it can also exceed 1.0, which we'll get to in a minute. Typically at rest, RER is about 0.8, okay? And like I said, you can exceed 1.0 during maximal exercise. So if someone's doing a max test, we'll start out around 0.7, 0.8, and it can get above 1 as we get near max or above max. All right, and so we use the way we're able to determine what kind of what kind of fuels being used is through something called stoichiometry, okay? Now, these are really complicated. It's not terribly complicated, but it probably looks complicated chemical equations. You'll never need to recreate these. You'll never need to use this for anything, but at least want to show you where we get these numbers from. So the chemical formula, if we break down a fatty acid to create ATP, is written here, okay? And notice the important thing here is that we use 23 oxygens and we produce 16 CO2s. And so 16 divided by 23, that gives us 0.7. So when we're just using fats, we are producing 16 CO2 for every 23 oxygen that we use. Now, if we do this with glucose, notice the equation's slightly different. In this case, for every 6 CO2 we use, or we produce, we're using 6 O2. And so that RER value is 1. Okay, that's where these numbers come from. All right, like I said, you'll never need to know these. You won't have to recreate them or answer this on a test, that sort of thing. But that's where these numbers come from. Okay, now it's safe to say you aren't always using fat or you aren't always using carbs, at least normally. Okay, there's always going to be a little bit of difference. And so what happens is, depending on your RER, we can estimate what percentage of fuel is coming from fats, what percentage is coming from carbs. Okay. And so we've got this table here. So we've got RER or RQ right here. And we've got how many calories are being produced or released for every liter of oxygen. Okay. And then what percentage of carbs are we using? What percentage of fat? So if I've done this table correctly, you add the far right columns, both of them together, it should add up to 100. Okay. And like I said, these tables ignore protein. We don't care about protein, essentially. All right. So notice that when we're at rest and have this RER of 0.7, we're only releasing about 4.7 calories for every liter of oxygen. Whereas if we are using all carbs, have an RER of about 100, or about 1, not 100, but 1, we're using a little over 5, or we're releasing a little over 5 calories per liter of oxygen. Okay. And so you can determine what your how many calories you're burning if you know the liters of oxygen that are being used per minute. And so let's just take this one right here. We're going to say 5.047. Let's say this is during max exercise, and so we're using 100 liters of oxygen per minute. O2 per minute. Sorry, it doesn't say that. Okay, and if we multiply 100 times that, then you're saying that we're releasing 500 kilocalories per minute. Okay. Now, that would be a ridiculous amount, so that's probably not a great example. Most people are not having or not using any. Actually, you're never using that much. So let me back up here just to make it a little more clear. So we're going to use these same numbers, but let's just say that I'm at max exercise or max effort here, and I am. Whoops, went back. And let's just say that I'm using 5 liters of oxygen. That's much more realistic as opposed to this 100 that I just said. Wasn't sure what I was thinking there. So if we go 5 liters per minute of oxygen, and just because it's hard to write, that's why I'm just going to do 5 liters. We multiply that by 5.047. Okay, that's going to get us a little over 20 calories per minute. That's more reasonable. Okay, so that's something that's close to max. All right, so just to give you an idea. All right, moving on. So how much energy you're using is dependent on what you're doing. The harder you're working, the more power you're producing, the more calories that you're using. And so this is where RER and VO2 can help us estimate how much energy are we actually using. But like I said earlier, this is only valid if we're at steady state and if we're at submaximal exercise. Okay. So steady state means that we're doing the same amount of work. Our body's caught up because every time you increase or decrease the intensity, there's a little bit of a lag, and your body's got to adjust things so it can meet the new demand. Okay, so once your body's met the new demand, you're at steady state. Okay, but it also has to be submaximal. And the reason for that is because as you get above maximal conditions, your RER can exceed 1. And this is for a variety of reasons, one of which is you're actually hyperventilating. Okay, and so you're actually releasing more CO2 than you are actually producing, and so it overestimates or overinflates what kind of energy you're actually releasing. And so like I said earlier, as we went through this, if you want to calculate the energy you're using, you need to know the following things. So your VO2, your RER, and you need to have a table, and then how long is your exercise. Okay, and so the formula is just this. If I were to have you use this formula or this table, I would give you this. I would give you the equation so you don't have to worry about memorizing the table or the equation. But just an example is, let's just say your VO2 is 2.3 liters a minute. Your RER is 0.83, so that's right here. So your caloric intake is 4.83. We got that there. And you did this for 60 minutes. Okay, so you would just go 2.3 times 4.838 times 60, and you get 668 calories during that hour. And so if you wanted to know how many calories were coming from carbs as opposed to fats, well, 43% of them are coming from carbs, so you go 668 times 0.438. Okay, and I'm not going to figure that out here, but that's how you would do it. And with that, we will end.